Welcome back to Hansen Theory. If episode 2 taught you about molecular forces, today you will see how those forces become something powerful, a visual prediction system. Because engineers do not fail due to lack of data. They fail because they cannot visualize molecular relationships. Hansen Space was created to solve this problem, not to look scientific, not to impress with 3D plots, but to convert invisible molecular interactions into something engineers can reason with. Let us begin with a mindset shift. Compatibility is not random. It is not trial and error chemistry. It is not luck. Compatibility is a distance problem. Two materials behave well together when their molecular interaction profiles are close. They behave poorly when those profiles are far apart. This is the foundation of Hansen Space. Instead of describing materials using words like strong solvent or weak solvent, Hansen placed every material inside a three-dimensional coordinate system. Each axis represents one molecular force: dispersion, polarity, hydrogen bonding. Every solvent, resin, polymer, or additive becomes a point in this space. Not physically in your lab, but mathematically representing real molecular behavior. Now think about what this means. When you select a solvent, you are not choosing a liquid. You are choosing a location in molecular interaction space. When you select a resin, you are not choosing a polymer. You are choosing another location. Compatibility is no longer a guess. It becomes a question of distance between 2 points. This is why Hansen theory is powerful. It converts chemistry into geometry. Now, let's talk about the solubility sphere. Every polymer has a tolerance zone, a region in Hansen space where solvents can dissolve or swell it effectively. This region is represented as a sphere. At the center of this sphere is the polymer's ideal interaction balance. Inside the sphere are solvents that match the polymer's force profile closely enough to be compatible. Outside the sphere are solvents that create mismatch and instability. This is not an artificial model. It reflects real experimental behavior. When solvents fall inside the sphere, polymers dissolve smoothly. When they fall near the edge, partial solubility occurs. When they fall far outside, failure becomes inevitable. Now here is where most engineers misunderstand the concept. They assume the sphere is fixed and absolute. It is not. The solubility sphere depends on molecular weight, polymer structure, temperature, and formulation environment. This is why two acrylic resins can behave differently even if they appear similar on paper. Hansen Space shows you trends, not guarantees. And that is exactly how engineers should use it, as a prediction tool, not as a replacement for thinking. Now, let's discuss why 3 dimensions matter. If solubility depended only on dispersion forces, a single axis would be enough. If it depended only on polarity, one line would work. But coatings involve multiple simultaneous interactions. 3 dimensions allow you to represent this complexity without oversimplifying reality. This is why 2 solvents with similar boiling points can behave completely differently, because their location in Hansen space is different. This is why 2 resins with similar appearance can show different compatibility behavior, because their molecular interaction profiles are not the same. Now consider what happens during solvent blending. When you mix solvents, you are not just mixing liquids. You are moving a point inside Hansen space. By adjusting blend ratios, you can steer your solvent system closer to the polymer center. This is engineering control, not guessing, not luck, not trial and error. This is why experienced formulators rarely rely on single solvents. They design solvent systems to occupy the correct region of Hansen space. Now, let's address an uncomfortable truth. Many engineers generate beautiful Hansen plots. They create colorful charts. They calculate distances.
But they do not understand what they are seeing.
They treat it as visualization software, not as physical reality. When you look at Hansen space, you should not see points and spheres. You should see molecules interacting. You should visualize polymer chains surrounded by solvent molecules. You should imagine attraction forces aligning or resisting. You should understand why a formulation is stable or unstable before testing it. This is the mindset shift. Hansen Space is not about drawing diagrams. It is about training your brain to think spatially about chemistry. Once you develop this skill, troubleshooting becomes systematic. Instead of changing random ingredients, you adjust force balance. Instead of repeating failed experiments, you reposition your formulation inside Compatibility Space. Now, let's connect this to industrial reality. Production failures rarely happen because of wrong chemistry. They happen because formulations drift outside acceptable compatibility zones. Temperature changes, raw material variation, solvent evaporation shifts, batch-to-batch differences. All of these cause movement inside Hansen Space. Engineers who understand this can predict stability risks early. Engineers who don't will always react late. This is why Hansen theory is not just academic. It is a production stability tool. In the next episode, we will go deeper. We will quantify distance. We will explain RA. We will explain red numbers. And we will show how engineers turn geometry into decision-making logic. If you want to stop reacting to formulation problems and start predicting behavior, stay with this series. This is Hansen theory.